This is a tutorial on electron configuration. It references material from Chapter 4 in Holt Modern Physics and Chapter 4 notes made by Ms. Moser. Those are available in the 2015 updated edition on PBWorks or Google Classroom. Okay, let's get started. So, if you remember, we've talked about a lot of different models of the atom. So we had everything from the very, very simple, spherical, uniform atom proposed by Dalton, up through the early quantum model proposed by Bohr as an improvement on Rutherford's planetary model. But the most modern understanding of the structure of the atom is the quantum model that comes out of the work of Planck and Einstein, de Broglie, Heisenberg, and Schrödinger. It's that tennis ball wrapped in yards and yards of cotton candy, a tiny solid positive center, and lots and lots and lots of negative fuzz, which is just the space in which little tiny electrons are buzzing around wildly. Okay, so now that we've established that, let's recall that Schrödinger's wave equations describe three-dimensional regions of space, and that those three-dimensional regions of space are areas where there's a high probability of finding an electron. These three-dimensional regions are called orbitals. And orbitals and groups of orbitals have got different amounts of energy. They actually exist in energy levels. This starts to sound a little bit like the Bohr atom, doesn't it? These energy levels are similar to the ones described by Bohr, though significantly expanded upon and improved by Heisenberg and Schrödinger. We'll dive straight into the crazy. Atomic orbitals have a whole series of quantum numbers which can be used to describe them. Huh? Well, think about this. So, if you're trying to find a house on a road and they all look remarkably alike, wouldn't it be really, really helpful if the houses had an address or some other way of telling them apart, some way to describe them as different from one another? That's really all that quantum numbers do. So, the first one that you should be aware of is n. It's shown as a lowercase n, and n is just the principal quantum number. N describes the main energy level that's occupied by electrons. And the numbers for n are always whole numbers. They start with 1, so we can have n equals 1, n equals 2, n equals 3, n equals 4, etc. On up to about n equals 7, but we don't talk about that much. If you are watching this tutorial as part of my class, n is really the only principal quantum number for which I expect you to know the letter. Alright, let's move on to the next one. L. L is the angular momentum quantum number, but I don't expect you to know any of that, and I don't really even expect you to know that. What you need to know is that the second thing that we are talking about with any given orbital is essentially the shape of the orbital. We'll get to that in a moment. M is the third in these quantum numbers that describe an orbital, and M is the magnetic quantum number. Once again, for my purposes, that's beyond the scope of the class, as is even remembering that this is M. What you need to know is that the third thing that we describe is the orientation of each orbital around the nucleus. So we're sort of imagining a big three-dimensional Cartesian coordinate system with an x and a y and a z-axis, and we're going to use some means to describe how the orbital is arranged in that space. That's pretty easy. The last thing we'll describe about the home of every electron is its spin quantum number. Now, we call it a spin quantum number, and we have to be careful, because you don't want to get the impression that electrons are really actually spinning. This is a way, again, of describing their attitude and position within an orbital. There are two values for spin, and we will talk about those. Electrons can be described as having spin up or spin down, and we show it with this little one-headed arrow. That's about it. Now, let's put these together. Okay, so we're going to build this chart together, and we're going to start off for each possible electron describing a location where it can exist. We're going to start off by naming the main energy level that it can be found on. So this is our n number, and we're going to start with n equals 1. This is the first main energy level. It's the lowest energy, it's the closest to the nucleus, and as we go up this chart with our n numbers getting bigger, the energy level is going to increase. So, for main energy level, sometimes called shell 1, n equals 1. And there's only one shape that exists on n equals 1. It's called an s orbital. And you can think of s as standing for sphere, because s orbitals are basically spherical. Every single level is going to have an s orbital, but that's all that exists on the first main energy level. Now, if you imagine a beach ball, and you imagine a Cartesian coordinate system, a little axis with an x and a y and a z axis, it doesn't matter how you rotate that beach ball around those axes, it's going to look exactly the same way. Well, guess what? There's only one s orbital on every main energy level, because it doesn't really have an orientation. It's spherical, hence the s. So, within that s orbital on the first main energy level, you can have two electrons. But it'd be way too confusing if these two electrons had exactly the same address. I mean, so far, we're saying that they both live at n equals 1, they both live in an s orbital, and they both live in the only orientation of s orbital that can exist. So we differentiate them based on their spin, and we say that inside that s orbital we have one electron whose spin we describe as up and one whose spin we describe as down. Hey, that was pretty easy. Okay, we've taken care of n equals 1. Let's move on to n equals 2. So at n equals 2, we have more energy. This is a higher energy level. This is the second main energy level, or second shell. So on the second shell, we have two subshells, or two shapes. We see our s orbitals again, still looking like a little beach ball, but now we add to that a new orbital, a p orbital. And p orbitals are very often described as dumbbells. That's our little p orbital. Now, in terms of orientation, what's really true is that as many ways as there are to orient an orbital around this little x, y, z axis, we're going to have an orbital to fill that orientation. So, while again on n equals 2 on the second energy level, we only get one s orbital, because it doesn't matter how you turn a beach ball, we get 3 p orbitals. They're oriented along the x-axis, the y-axis, and the z-axis. So that's pretty hard to draw, so we usually just draw it as though it's sort of leaning over. Well, within each of those orbitals, we can have two electrons. And each of those electrons has to have its own individual sort of address. So we have one in the 2s with a spin up, and one down, up and down, up and down, up and down. The drawing does get kind of weird. That's it for the second main energy level, or the second shell. Two shapes, 4 actual orbitals, and 2 electrons in each one. Let's go up to n equals 3. On the third main energy level, we have an s orbital, it's the 3s orbital. We have p orbitals, and now we add one more. We add a d orbital. And D's Well, they're kind of hard to describe. Sometimes called double dumbbells, so they kind of look like two p orbitals put together. Well, there are 4 that look like that, double dumbbells. Then there's one really weird one that looks like 2 drumsticks and a donut. They just get strange. So suffice to say, there are 5 d orbitals. To say that drawing them gets a little bit weird is an understatement. So we now have our 1s orbital on the third main energy level, 3 p orbitals on the third main energy level, and 5 d orbitals on the third main energy level. And each of them gets, guess what? Yep, that's right, 2 electrons. One with spin up, one with spin down. Okay, it's getting crowded in here. Let's move up to the 4th main energy level. Add to your S, P, and D an F. An F is, quite frankly, too weird to draw. The important thing to know is that there are 7 different orientations that an F orbital can take around the nucleus. When I say they're too weird to draw, I mean it. Do a Google search. As you may have figured out by now, within each of those orbitals on the 4th main energy level, we have 2 electrons, one described as spin up, one described as spin down. Okay, what does this all mean? Well, what it means is that we can put an exact street address onto any electron in any atom. Did you notice a pattern with the number of electrons that every orbital seemed to hold? Did it seem to get repetitive? Well, as a matter of fact, there's a very definite number of electrons that any orbital can hold. Any S, any P, any F, any D, any G. Yes, it gets weirder than F. Every orbital can hold 2 electrons. There is no orbital that can hold more than 2 electrons. The maximum number of electrons an orbital can hold is 2. All orbitals, no matter what they look like, no matter how weird they are, can hold 2 electrons. So, how many electrons can any single orbital hold? 2! Good job. So, you may have noticed that the first main energy level, n equals 1, has 1 shape of orbital, 1 total orbital, and 2 total electrons. The second main energy level, n equals, whoops, that should be a 2, has 2 shapes, 4 total orbitals, and 8 total electrons. The third main energy level, n equals 3, has 3 shapes, 9 total orbitals, and 18 total electrons. Do you see a pattern here? Well, if you had to make a bet, main energy level 4, n equals 4, has how many shapes? What's that you said? You said 17? No. 4. 4 shapes. Guess how many orbitals it has? 16 total. And it's got 32 total electrons. Can you see the mathematical pattern here? We can predict how many shapes, orientations, and electrons any main energy level can hold. The number of shapes is just equal to the number of the main energy level. So n equals 1 has 1 shape, n equals 4 has 4 shapes. The actual number of orbitals on any main energy level is equal to the number of the main energy level squared. So hence, energy level 2 has 4 actual orbitals, energy level 3 has 9 actual orbitals. And since each orbital can hold 2 electrons, the number of electrons on any main energy level is 2 times n squared. We'll keep looking at it. You'll get used to it. We'll stop there for now, and we'll pick up our next tutorial with electron configurations. That's it, folks.